All right, welcome back, everybody. Today we're going to get going with Chapter 7, dealing with similarity or similar geometric figures. Now, before we get into similarity in the next lesson, we're going to introduce two concepts for you. In the first one, ratios and proportions. Now, these are important concepts on their own right, a lot of practical applications to them on their own, which we'll see today. But also, we're going to use these two ideas to build off of into the similar geometric figure stuff we do in the next few lessons. Okay, so let's talk about ratios and proportions. Objective to write ratios and solve proportions. Here we go. All right, so now when I say ratio, what we're talking about is just the comparison of two quantities by division. So anytime you compare two numbers using division, you're writing a ratio. And I'm going to say this is something we do all the time in the real world. Let's say I want to figure out what my batting average is, and I have, let's say, 3 hits for my 20 at-bats. Let's say I'm not very good at baseball. 3 over 20, okay, 3 divided by 20, if I divided those numbers, that would give me my batting average, essentially my ratio of hits to at-bats. Okay, we talk about recipes, and let's say I have a recipe that calls for a ratio of 1 onion for every 3 tomatoes. Okay, by knowing that ratio, what I'm able to do is scale my recipe up or down depending on how much of it I want to make. Okay, or we could look at something like my height. Let's say I'm 5'10", like my driver's license says, over 180 pounds. Okay, I could look at the ratio of my height to weight, which is essentially what you do when you find body mass index. Okay, we can come up with a whole bunch of other ones, but these are all examples of ratios we look at in the real world. Okay, let's say you can write a ratio of two numbers, A and B, where B is not 0, because you can't divide by 0, in 3 ways. We can write it as a fraction, A over B, or we can write it with a semicolon. We'd read it as just as A to B, or we can actually write out A to B. They all mean the same thing, A divided by B. So let's jump into problem 1. We're actually writing some ratios. Part A says a model is made of a car. The car is 9 feet long and the model is 6 inches long. What is the ratio of the length of the car to the length of the model? Okay, well, why would we want to figure out this ratio? Essentially, it's going to tell us how much bigger the car is than the model. Okay, it gets into the idea of a scale factor, which we'll talk more about tomorrow. So let's write that ratio. And now it's not a huge deal for the real world, but if we want to get the question right for the homework and for the tests, let's make sure we write the ratio in the order the question's asking for. So this one's saying we want the length of the car to the length of the model. So meaning that when I write my fraction, I'm going to put the car on top and the model on the bottom. Okay, so in this case, the car, it says, is 9 feet long. So we'll say 9 feet. All right, over the length of the model, which is 6 inches. So I can say the ratio of the length of my car to the length of my model is 9 feet to 6 inches. Okay, now at this point, our ratio doesn't really tell us much. Okay, if I divided these two, it's not really going to be very meaningful, just because one of the measurements in feet, the other one's in inches. They're in different units. Anytime you have different units, you want to convert them to the same unit. So what I could do is I could go either feet to inches or inches to feet. Just to avoid fractions, 6 inches isn't a whole foot. I'm going to go from feet to inches. So we're going to multiply my 9 feet by 12 to give me 108 inches over 6 inches. And then once I'm in terms of the same unit, we can actually do the division. We can reduce. 108 divided by 6 is 18. And we'll just leave it as 18. We'll think of the inches on top and bottom as canceling out. Okay, so we could say the ratio of the length of my car to the length of my model is 18, or we could say 18 to 1. In other words, the actual car is 18 times the size of the scale model. All right, so that's how you take two quantities and write a ratio. Problem B is the same idea. So why don't you take a minute, pause the video, work through part B, and then hit play to run through the answer. All right, part B says the Empire State Building in New York City is 1,250 feet tall. A model of the tower is 60 inches tall. What is the ratio of the height of the model to the height of the actual building? Okay, so for this ratio, we want to do height of model to height of the actual building. So we'll put the model on top of our fraction and the building on the bottom. It says the model is 60 inches tall, and the actual building is 1,250 feet tall. And once again, I either need to convert my inches to feet or feet to inches. Now, it doesn't matter which one you do, you'll get the same ratio when you reduce it down either way. Okay, but for this one, since I don't want to end up with huge numbers, I'm going to divide the 60 by 12 instead of multiplying the 1250 by 12. So that'll give me 60 inches is the same as 5 feet over the 1,250 feet. And once again, we can think of the feet as canceling. And I can just reduce this 5 over 1,250. I can just take 1,250 divided by 5. And when I do that, I get 250. So we can say my ratio is 1 over 250. Which means that the model is 1/250th the size of the building. Or in other words, the building is 250 times bigger than the model. All right, next up, let's take a look at some applications of ratios. Problem 2, part A says members of a school band are buying pots of tulips and pots of daffodils to sell at a fundraiser. They plan to buy 120 pots of flowers. The ratio of tulips to daffodils will be 2 over 3, or 2 to 3. How many pots of each type of flower should they buy? All right, so here we have a classic business situation. Let's say we know how many pots we need to sell for the fundraiser, 120 pots to reach whatever our goal is. And let's say we know that more people buy daffodils than tulips. And from experience, we know that they buy tulips to daffodils in the ratio of 2 to 3. We can use that information to figure out how many each type of flower we want to buy. Okay, the trick for this is I'm going to take these two numbers, 2 and 3, and add x's to them. So I'm going to say 2x plus 3x. So x is going to kind of act as a scale factor for us, is equal to the total, 120. And what I can do then is solve for x and then use that x to figure out how many pots of tulips and how many pots of daffodils I actually need to buy. Okay, anytime I'm given a problem where I have the ratio and the total of what we want, I can set it up like this. We'll look at a few different examples as we go through problems 2 and 3 here. Okay, so let's solve this. 2x plus 3x is 5x. So I can divide both sides of that equation by 5. And I end up with then x is equal to 24. So we have x equals 24. Now, 24 is not my answer. What 24 is going to be is it's going to act as a scale. That's going to allow me to find the actual pots of tulips and daffodils. So let's show you how we can do that. If I want my tulips, what I'm going to do is I'm going to use the 2, or kind of the 2x part of my equation. We'll say the tulips are equal to 2 times my x, which is 24. So in other words, we need 48 pots of tulips. And then same idea for the daffodils. That came from the 3 number for my ratio, or the 3x part of the equation. So my daffodils will be 3 times that 24. Or in other words, 72. We'll have 72 pots of daffodils that we need. Okay, if I want to check this answer to make sure I'm doing it right, what I could do is, 1, check that 48 plus 72 equals 120. Looks like we're good there. And then also, if I took this and reduced it, 48 over 72, it should reduce down to the same 2/3 we had here. So I know I'm doing this one correctly. All right, problem B is a similar example. Take a minute, pause the video, run through part B, and then you can hit play and we'll run through it together. All right, part B, completely different situation, but same type of problem. It says the measures of two complementary angles are in the ratio of 1 to 3. Okay, what are the measures of the angles? So once again, I have a ratio of something, 1 to 3, and I know the total. Okay, these angles are complementary, which means they add to 90. Little vocab from first semester. So what I can do is I can take both these numbers and hook them to an x. I can say 1x plus 3x is equal to 90. We'll solve that for x then. X plus 3x would be 4x equals 90. We'll divide both sides by 4 and end up with x equals 22.5. All right, then again, we can use that 22.5 to find the actual measure of the angles. Okay, we don't actually have any angle names. I'll just say angles 1 and 2. We could say angle 1 is equal to 1 times the x. Okay, for the 1x part of the equation. In other words, just 22.5 degrees. And the same idea for the second angle. That's going to be 3 times the x. So 3 times 22.5. Which will give me a 67.5 degrees. Again, we could check that by making sure these two add to 90, which they will. And if I find the ratio of 22.5 to 67.5, I'd find that it's 1/3, okay, or 1 to 3 like we started off with. Okay, next thing we're going to talk about is the idea of an extended ratio. An extended ratio is just something that compares 3 or more numbers together. So for example, here if I had 3 numbers A, B, and C, I could write the ratio as A to B to C. And again, it's just a way to make comparisons of more than 2 numbers at a time. So let's look at using extended ratio. Problem 3 part A says the lengths of the sides of a triangle are in the extended ratio of 3 to 5 to 6. The perimeter of the triangle is 98 inches. What's the length of the longest side? So this is going to work out the same way as our last problem did. We have a ratio of what the parts are coming in, 3 to 5 to 6. And we have the total, the perimeter, 98 inches. So what I can do again is just hook x's to all 3 of these numbers. We can say 3x plus 5x plus 6x is equal to the total, 98. Once again, we can solve that for x. 3 plus 5 is 8. 8 plus 6 is 14. So we can say we have a 14x is equal to 98. And then to get x by itself, we'll divide both sides by 14. Which leaves me with x, kind of my scale value, of 7. And then I'm not looking for x. What I want to know for this one is the length of the longest side. Okay, that longest side is going to correspond with this 6x part of the equation. So what we'll do is we'll say the longest is equal to 6 times the x. In other words, 7, which would be 42 inches. All right, so that's how we can use an extended ratio in the same way that we used a just regular ratio. in the last problem. Okay, part B is the same idea. Why don't you take a minute, pause the video, run through that one, and then hit play to check your answer. All right, so part B says the angles of a triangle are in the extended ratio 2 to 3 to 5. What's the measure of the smallest angle? So again, I've got my ratio. I can just hit x to my numbers. We'll say 2x plus 3x plus 5x. And then now this problem doesn't explicitly give me the total, but we're talking about angles of a triangle. I know the angles of a triangle always add to 180. So we can say 2x plus 3x plus 5x equals 180. Okay, solving for x, 2 plus 3 is 5. 5 plus 5 is 10, so we can say 10x is equal to 180. Divide both sides by 10, and we end up with x equals 18. And then what are we looking for this time? We want the measure of the smallest angle. So for this one, we'll go to the smallest part of our equation, the 2x. So we'll have 2 times our x value, which is 18, which will give me a 36. We're talking angles, so we can say 36 degrees. All right, now the other thing we're going to talk about today is a proportion. I'm going to say a proportion is an equation that states that two ratios are equal. So for example, if I have the ratio 1/2, that's the same as 2/4. That's equal to 2/4. 2/4 reduces to 1/2. Okay, that's an example of proportion. Now, what we're going to look to do is solve proportions for x values. Okay, we want to figure out the x values that finish off a proportion. So for this example, instead of a 2, we could put an x there and solve and figure out that's 2. And to do that, we're going to use something called the cross product property. It just says that in a proportion, the product of the terms that are diagonal across the equal sign from each other are the same. Okay, so in other words, if I have a over b is equal to c over d, b times c, one of my cross products, will be equal to a times d, the other cross product. Okay, reason for that, real quick, if I have a over b is equal to c over d, if I have this correct proportion, and I multiply both sides of this equation by b, the b's on the left will cancel. And if I also multiply both sides by d, the d's on the right will cancel. So what I'm left with then is kind of backwards from what we see here, but a times d on the left is equal to c times b on the right. Okay, so the cross product property is just basically canceling out the division for us. So let's look at how to solve proportions. In problem 4, what's the solution to each proportion? In other words, for the first example, we have 6 over x equals 5 over 4. We want to know what x value makes this proportion correct. Okay, what makes it hold true? And to do that, what we'll do is we'll take the cross product, or we'll cross multiply. I'm going to say x times 5 is just equal to 5x. And that's going to be equal to the other cross product, 6 times 4, which is 24. So we'll cross multiply, then divide. Divide both sides of this equation by 5. We don't end up with a nice number. What we end up with, we could say x equals 4.8. Okay, so when x equals 4.8, this proportion will be true. These two ratios would reduce down to the same thing. They'd be equal to each other. All right, b is the same idea. Why don't you take a minute, pause the video, and figure out what b is equal to. All right, so running through b, taking our cross product, 3 times x, we can say is 3x, is equal to 5 times 8, which would be 40. So cross multiply, then divide. Divide both sides by 3. And we end up with x is equal to 13.3 repeating. All right, in part C and D, we're going to do the same thing. We're just going to solve some uglier looking proportions. They'll work the same way though. I'm going to cross multiply. So let's say I have 9 times y, or 9y, is equal to y plus 4 times 3. And I'm going to write that as 3 times the quantity of, or parentheses, y plus 4. I'm going to write it with the parentheses to make sure I remember to distribute the 3 to both the y and the 4. So solving then, it's a little more complicated than just cross multiply and divide, but basically the same thing. We have 9y on the left is equal to 3y, okay, remembering to distribute, plus 12. And then to get the y by itself, we'll subtract 3y from both sides, which gives us a 6y is equal to 12. And then we'll divide both sides by 6 to end up with y equals 2. All right, when you get an answer to an uglier one, you can check and make sure that works. When y is 2, we have 2 plus 4, which is 6, 6 over 9. That would reduce down to 2/3, which would be the other side. When y is 2, we'd have 2/3. Because just like with any equation, you could plug that in to check. All right, D is the same idea. I want you to take a minute, pause the video, run through part D, and then hit play to check your answer. All right, running through D then, let's take our cross products. 2n times 7 is going to give me a 14n, which will be equal to 4n plus 1 times 3. We'll write that as 3 parentheses 4n plus 1. And we can distribute on the right, which will give us a 12n plus 3. On the left, we still have the 14n. And solving, I'm going to subtract 12n from both sides to give me 2n is equal to 3. And then we can finish by dividing to end up with n is equal to just 3/2, we could say, or I suppose 1.5. All right, the last thing we'll do in this lesson is look at some properties of proportions, or look at ways we can rearrange proportions to come up with equivalent proportions. So let's say that A, B, C, and D do not equal 0, so they're numbers. Property 1 says that A over B equals C over D is equivalent to B over A is equal to D over C. So is equivalent to, in other words, if one proportion is true, the other one will also be true. Okay, notice the only difference between these is the second proportion is the first proportion flipped upside down. So this is telling me that I can flip my proportions and they'll still work out. And as an example quick, if I have the proportion 1/2 equals 2/4, we'll use that example again. Okay, well if I flip that to 2 over 1 is equal to 4 over 2, that is still true. Okay, flipping the proportions leaves me with still a true proportion. Okay, 2 says that A over B equals C over D is the same thing as A over C equals B over D. Now notice with this one what we did is we took one of the essentially cross products and flipped them. We flopped the B and the C between these two proportions. Okay, we could show you why that's true with some multiplication, with some kind of rearranging those proportions. We're not going to get into that though. The reason that this is helpful is it's going to allow us to set up proportions in different ways, especially as we get into real world situations, and still come up with the same answer. Okay, last one. A over B equals C over D is equivalent to A plus B over B is equal to D plus D over D. So what I'm doing here, notice, is I'm taking the denominators for both these proportions and adding them. Essentially, this is saying is that if I add the same thing to both sides of my proportion, in other words, adding 1, because B over B would be a 1 and D over D would be a 1, I still get something that's true. All right, let's look at using those properties quickly. Problem 5 says, in the diagram, x over 6 equals y over 7. What ratio completes each equivalent proportion? Okay, so I actually don't need my diagram. We'll just focus on the proportion here. So if x over 6 equals y over 7, we want to know what x over y is equal to. Well, I can get x over y by basically switching the y and the 6. One of the properties we just showed you said you can do that, so we could say that x over y is equal to 6 over 7. Okay, that would be how we could finish that proportion off. Okay, second example, we have 6 over x, which is the first ratio flipped upside down. We said that we can flip proportions and it'll still be true. So I can say this is just equal to 7 over y, flipping the second ratio. All right, last one, we have y plus 7 over 7. Okay, basically we added the denominator to the numerator of my second fraction. So I can just say that this is equal to x plus 6 over 6. And that's essentially taking this proportion and just adding 1 to both sides of it. Okay, so that's it for our section on ratios and proportions. Important stuff. We'll build on that through the rest of the chapter. Start working on the homework. Start getting your practice in. Let us know if you need help. And we'll see you next time for the next lesson here.